The first thing we can do is something that's often done, and we'll see this for both the vibrational and the rotational partition function, is often we can collect a lot of the constants into one term that we call a temperature, because it ends up having units of Kelvin, all the constants. So we define a vibrational temperature that's related to the vibrational frequency that we have. So our vibrational temperature is defined, we call it capital theta vib for vibration, is equal to h nu over the Boltzmann constant. All right, so that's our constants here. H nu shows up both here and here, and then the Boltzmann constant is part of B, right? Because sorry, not B, beta, because beta is equal to 1 over kBt. So if we rewrite this partition function in terms of the vibrational temperature, we get that Q vib is equal to e to the minus theta vib over 2t for the term on the outside times 1 over 1 minus e to the minus theta vib over t. So you can see, this is going to be relative to a temperature, how much you get a vibrational contribution to the energy. Okay, what can we do with this partition function? There's a couple things. Well, first we can, of course, just like we can with any partition function, we can find what's the average energy, right? We have the formula for that the average energy, and here we're just looking at for the vibrational energy. We could do this with any of the other partition functions as well, like the translational, which we've already done in the previous chapter. If we write this in terms of the temperature version of this equation, we get the average energy is equal to kBt squared over d log Q vib dt. This is the temperature version of, we've previously seen this as negative d log Q d beta. All right, so this is just converting from beta to t. We get this kBt squared on the front. Just as a reminder, I'm pretty sure I showed that in the previous videos. Okay, so let's go ahead and use this partition function we have here and this equation and find out what's the average vibrational energy contribution. So let's first look at what's the log of Q vib. Okay, so the term in front is just a constant, right? We're just going to have a natural log of our exponential term here. We'll do it in red this time. Natural log of that is just whatever's up here in the exponent. So we'll get negative theta vib over 2t. And then we'll have a second term plus the natural log of 1. So that's our numerator of this fraction here. And then we'll get what's in the denominator, minus the natural log of 1 minus e to the minus theta vib over t. All right, that was just sort of separate things out. So one thing to notice here is that, of course, we have a term that doesn't have a t in it. So when we take the derivative of the natural log with respect to dt, the first term is pretty straightforward. We're going to get we're going to get theta vib, positive theta vib over 2t squared, because this is the same as t to the minus 1. So we're just taking the derivative there. The second term goes to 0 because there's no temperature term in there. And then we need to take the derivative of the final term, the natural log 1 minus e to the minus theta vib over t. For this, we're going to need to use the chain rule. So this gets a little bit messy, but we're going to have a minus. The derivative of the natural log of our function in here is 1 over 1 minus e to the minus theta vib over t. Right, so we've taken the derivative of what's inside. Then we need to take the derivative of, so the derivative of the whole thing times the derivative of just what's inside of here. So the derivative of 1 minus e to the minus theta vib over t. All right, so we're going to end up with a theta vib over t squared times minus e to the minus theta vib over t. All right, and that's from taking the derivative of the exponential. Okay, so after all that, our average vibrational energy is equal to this up here times kBt squared. All right, so we'll get kb t squared times theta vibe over 2t squared plus theta vibe over t squared times, reading my notes here are a little bit messy, e to the minus theta vibe over t divided by 1 minus e to the minus theta vibe over t. Okay, so how can we simplify this? We multiply it through by kBt squared. This term on the right, we can rewrite this by multiplying by, if we take this term, just following what I have here in my notes, e to the minus theta vibe over t times 1 minus e to the minus theta vibe over t. If we multiply the top and bottom by e to the positive theta vibe over t, this lets us get rid of the exponential in the numerator and gets us to the next version of the equation that I have, which is where we have kb times theta vibe over 2 plus theta vibe, t squareds cancel again, times e to the positive theta vibe over t minus 1. And that simplification to this comes from this down here. This leads to we have just this in the denominator. Okay, so that is our vibrational contribution to the energy. So it depends on that vibrational temperature. We have one term that doesn't depend on temperature at all. So this is what we call the 0-point energy. And this is the energy that comes from just the fact that our molecule is always vibrating a little bit, and there's actually no way to prevent it from doing that. If you plug in V equals 0 into the energy equation we had earlier, there's still a small amount of energy. You can't get rid of that. And that's where this term comes from. And then we have the second term that this shows our temperature dependence. Okay, and in the next video, we're going to take one final look at the vibrational energy. We're going to look at how does the vibrational energy contribute to the heat capacity, the change in internal energy with respect to temperature, which we can look at based on this equation by differentiating this with respect to temperature.